Everyone. My name is Frederik Rapp. I'm from the Fraunhofer IPA, and I will talk today a bit about the automatic generation of quantum neural networks. And I will briefly start with a motivation for this talk, and this is why are quantum neural networks or parameterized quantum circuits or feature maps. This is basically the same word for, or three different words for the same thing, which is just the context. Is like if you use a kernel method, it's most often called a quantum feature map. You can also call it, parameterized quantum circuit or a quantum neural network. And the motivation is why are they so important for QML. And in the NISQ era especially, from an algorithm perspective, we have to think about what kind of data we have and what kind of algorithm we actually want to use. And especially in the NISQ era, it's mostly hybrid models which try to process classical data with a quantum algorithm, where most often in a machine learning context, it's just a small part of the algorithm which is outsourced on the quantum computer, for example, the computation of the kernel matrix. And to map then the classical data onto the quantum state space, we need these quantum circuits. And they can be parameterized, which enables optimization later on, for example. And they usually consist of rotational gates, which is why I depicted this little picture here. As you can see, like we have some classical data points, and we have to map them through these rotational gates onto the Hilbert space on which the quantum computer acts. And they are in general defining the hyperparameters and the performance of the quantum machine learning model. I showed you here a little picture of a typical literature parameterized quantum circuit, which you can see it consists of some rotational gates with 3 parameters and some rotational gates which map the data point x onto the quantum state space. And the general finding of the state-of-the-art research is that if we want to have quantum models which perform better than classical models, we have to tailor these circuits to the data we have. And this process is far away from being trivial. And also in the future, we have probably way less experts on the topic. Like, imagine you have some data set which is already pre-processed with your visualization tool of choice. You get the data set, I show it to you, and you can have, there's no expert which then can say for this data set, I need to have first this rotational gate, and then I put a Hadamard gate, and then a CNOT entangling gate, because it's way too abstract for us to grasp. And also in the research right now, you see many different feature maps or parameterized quantum circuits or quantum neural networks, which are most often chosen heuristically. They're not tailored to the specific data set. And this motivates to create custom feature maps /QNNs/PQCs, which are tailored to the data set. And I, in my project, use reinforcement learning for this. Lucky you already got some introduction to reinforcement learning in the talk earlier. But I want to mention, and I need to mention, that in the earlier talk, you heard reinforcement learning from a quantum perspective, so quantum reinforcement learning. This is the part we now use reinforcement learning for quantum machine learning. So the reinforcement learning part actually stays classical. And just maybe there's some new listeners, so just briefly, in reinforcement learning, there's an agent interacting with an environment by taking actions and receiving rewards and observations back from the environment, and it tries to learn by finding some long-term optimal policy, which has to be defined by the programmer, so the environment and the action space. And what's our goal is we want to build some environment based on a QML method. Therefore, we implemented a Python library, which is called sklearn, and it allows us a smooth interaction with scikit-learn interfaces for those of you who are familiar with the scikit-learn library of the classical machine learning. And so the sklearn library enables us easy integration. We can build quantum kernels and quantum neural networks with this library. And it allows us an easy interaction with the stable baselines library, which is a typical reinforcement learning library from OpenAI. And we define our QML environment and put it into the stable baselines library. And so the overall idea to show it to you is then, basically, we want the agent to select different gates of a parameterized quantum circuit, given a specific data set. Then a QML model is performed, and we can obtain, for example, a performance metric of the QML model, in this case, for example, a classification task. And we can feed the performance as reward to the agent, and he then chooses different gates and tries to tailor the circuit to the given data set. And the goals and the challenges are, as always in reinforcement learning, we have to find an appropriate reward setting, also find a suitable action space. Then there are plenty of different reinforcement learning algorithms in general, which one could compare with each other. And as already mentioned in the talk before, reinforcement learning is quite sample expensive, which means it can take quite a while training the reinforcement learning algorithms. And our goals are, first of all, that the reinforcement learning agent is able to generate a suitable encoding circuit for a given data set. And the long-term goal is that we have a reinforcement learning framework which is able to generalize, which we can feed different data sets to, and which gives us tailored quantum neural networks / parameterized quantum circuits. And therefore, we choose two different approaches. One approach is, as you can see here, the reward based on the performance metric of a given QML method, which we have to choose. And the other approach is basing the reward on pure properties of the quantum training kernel matrix, basically. There are different metrics which one could consider. One is the geometric difference, for example, and I right now use the so-called prediction error bound. And in general, we tested two different kind of reinforcement learning paradigms, which is one is model-free approaches and one are model-based approaches. The results you're going to see right now are all obtained with using model-based approaches. And as a first test data set, we used the so-called quantum fashion MNIST data set. For those of you familiar with machine learning, the fashion MNIST data set is a quite classical or typical benchmark data set in machine learning. And overall, the quantum fashion MNIST data set is obtained by putting the data of the fashion MNIST data set through a quantum circuit already, which makes the data basically synthetical quantum data. And it turns the classification problem into a regression problem. And then our framework generally allows for testing QNNs as kernels of the type of fidelity quantum kernel or the so-called projected quantum kernel. And the automatic generation of the networks is now done by the quite sophisticated mu0 reinforcement learning algorithm, which is an algorithm developed by the DeepMind team and really one of the state-of-the-art reinforcement learning algorithms. And for you to get a little intuition how everything works, is I depicted you a common literature feature map, like different libraries as PennyLane or Qiskit offer types of these feature maps. They call it sometimes strongly entangling feature map, sometimes data re-uploading feature map. Yeah, but just in general for you to get intuition. And there would be a result how a tailored feature map looks from the mu0 algorithm. This is basically just that you can see that there is like, it's not completely like nonsense type of network architectures which are coming out of the reinforcement learning framework. And you can clearly see that it is problem specific and not as the like typical architectures. And then I will provide some results right now, which is the plot of predicted values over the actual values. And you can see, like, first I tested a classical RBF kernel-rich, RBF kernel-based kernel-rich regression. And it performs good on training, bad on testing. To be fair, for the classical model, the quantum fashion MNIST data set is a data set out of research, pretty popular, but it is designed to be hard for classical methods because it's like a synthetic quantum data set. But for me, the important part is that it serves as a benchmark for, like, I take several literature, like feature maps or architectures out of the literature. I test them. The best obtains a score of a testing score of 0.75 in the R2 score. And as you can see with the tailored feature map you could see before, this one here, the test score is the best. So far for the quantum fashion MNIST data set, the reinforcement learning framework was able to come up with a tailored feature map for the problem. Yeah, and in the end, I want to give you a brief outlook. It's like, of course, first of all, I have to consider more data sets, different data sets. Have to test the framework over and over again. Then there is, the tricky part is how to incorporate the variational parameters you can have in the PQCs into the reinforcement learning part. Like, either do you optimize them in every step, or do you just like choose them randomly, get the architecture, then do the optimization of the parameters in the end. And then there are also loads of different metrics, performance metrics to consider than the one we choose now, because in reinforcement learning one can basically always tune the reward and also the action space. And overall there are also loads of different reinforcement learning algorithms, for example, other different tree search approaches which I could consider. For example, the mu0 algorithm was based on a Monte Carlo tree search, but there are like many other methods, so it's a very explorative task right now. And yeah, with this I want to thank you for your attention. If you have any further questions, feel free to come to the Quantum BV booth and discuss it in more detail. So yeah, thank you very much.